Thermal questions?
I just did the homework. Look at that. Well, it was from yesterday.
Okay, today we tackle and largely fail at solving a tremendous enigma, the enigma of the Pauli, Dirac, Fermi anti-symmetrization. And we'll do the best we can given the enigmatic nature of this, but I think there's some light showing a little bit on this problem that might be helpful for our future. Remember that we are talking about an experiment, or at least we're dreaming about an experiment involving the C60. And the C60 will make this enigma shine as it has never shined before. The fact that C60 with carbon-12 is totally Bose as far as the nuclear spins go. They're all spin zero if you get a pure carbon sample. 1% of the carbon in nature is, about 1% is carbon-13, that's fermion. So if you make buckyball out of carbon-13, that's an expensive proposal, but we hope to do it. You've got a different animal entirely. So we want to talk about that enigma today. So the philosophy aside, there's some computational things that we want to do today as well. First of all, looking over on the other screen is the freshed out reference section for page 2 with the main things at the top as usual. Then there's a page for excerpts from the class, both the papers and the book Quantum Theory of Computer Age and the Principles of Symmetry, Dynamics, and Spectroscopy that relevant to parts of this class that we've yet to cover, but also we've been covering. And then finally, some stuff that's just outside of the area, but still relevant and interesting, and try to highlight things that are beyond the average, shall we say. So today, as I say, marrying spin, particularly spin 1/2, that's the spin of an electron. We're still talking about atomic physics here, and the orbital motion, which will become rotational moment and motion and nuclear spin as we get back to molecules in a couple of classes. So coming over here to this screen, the first thing I really want to make clear is that in any situation that involves Fermi spins, also integral spin, this idea of separating the orbital properties, I mean symmetry properties, but also the dynamics that an orbital involves, and on the other side, sort of as though it's a different animal completely, the spin properties of that object, whatever it might be. Here we're thinking the electron, or electrons. In this case, we would imagine 4 electrons making up a state of, well, we're mostly talking about nitrogen atom with our Pea Shell, but the next entry in the Pea Shell with P the 4th is oxygen. So what we're breathing here is part of the class. So this would be an oxygen problem right here. But I'm most worried in connection with the so-called exclusion principle, and we have to be aware that it's really not something we've proved yet, even at the highest levels of physics, and that is a shame. We should have done this by now. But also learning to apply it is not done, I think, with all of the grace that this idea or this property of nature deserves. So today I would like to go over just the idea of how, I say the word marry here, how do you marry these separate properties in your formalism or your description of something that needs that marriage in order to make sense of physical phenomena that occur in both atomic and molecular, and also most notably nuclear physics. That's not mentioning yet high energy physics, where it also plays a major role. So we've been looking at the triplet P that comes out in some of the stuff that comes in oxygen. With nitrogen, we had one less box here and one less box there. The P doublet that came up with the last lecture is what we're going to look probably more closely at in just a few pages here. In any case, the idea of putting this together, and then how is it that we can do this, and then when it finally fails because of spin-orbit interactions and things like that, where finally the spin says, hey, I want to be part of this more than just setting the symmetry I want to be in the dynamics. How do you do that? So building a wave function that is totally antisymmetric from things that are not is a bit of an art, and that's one thing I want to point out toward the end of the lecture today, just how that happens, how we can think about it. How does the identity of the particles make that possible? And we'll be finding ways other than this desperate, where the marriage is kind of at arm's length. When the marriage is, shall we say, consummated, is when you actually write these arrows next to the orbital state number. When you do that, when you make something that's called the Slater determinant, then you're getting closer to what nature really experiences. So we have to do that in order to get this. Before I do this, I just wanted to show the Pea Shell in a nutshell. And it's a pretty big nutshell. There it is. Okay. We start off at the top here with the very lowest state of the triple P, the P to the third power. And let me bring the other computer up to speed here so that we can look at the whole thing where it infringes on the screen at the top here, and that one's pretty good at the top. Anyway, the quartet, as we haven't really said that much because it's pretty easy to calculate the angular momentum and the quadrupole repulsion energy that goes with this one, and it's essentially zero. Certainly zero as far as the orbital angular momentum. But when the orbital angular momentum gets to be zero, this Pauli-Dirac-Fermi thing says, aha, spin gets to play. And so you have a very antisymmetric sort of coupled up orbit to make no angular momentum in the z component or in total, with this vertical box of 1. Remember what 1 means. 1 means angular momentum mz equal to 1. But then there the numbers, as the 2 and 3 and 4 later on go, the mz goes down, so the 2 here is 0, and then the 3 is -1, so this is orbitally paired to 0. Whereas here the spins are free to play, and play they do. Each of the 4 quartet states correspond to spins being turned from up to down, down, and finally to down, down, down. And that accounts for change in the z component here, which I've indicated of the spins by the Greek letter mu. It's not too common, but I've seen it in a number of places. In any case, this is the whole picture, and I tried to get, you see here, all of these are states where the total z component of momentum for the D shell is 2, and then 1, and when 1 comes up, then the P doublet says, hey, I want to play now. And so the middle of this consists of this, this. Okay, here's M equals 0. That's sort of the center now of the states that are in this shell. And then finally, I didn't have enough room here to stick the M equal minus 1 row, but it doesn't look too much difference from the M equal plus 1 row of states. So one of the things that we haven't emphasized a whole lot here is that when you apply the lowering angular momentum operator, and that's E elementary operator 1, 2, plus the E 2 to 3 operator, destroy a 3, create a 2, as I do that and come down from this highest state here for the angular momentum 2 doublet, as I come down to here where the angular momentum is less, I don't describe it by just a single tableau anymore. For the P and the D both, I describe a sum, 1 plus, or this one, 1, 1, 2 plus 1, 1, 3, those are both giving us M equal to 1. That's 1 plus 1 plus 0. Here, let's see if I made a mistake there. I have indeed, this is a typo. This should be a 1, 2, and this this should be a 1, 3, 3. I don't know how I made that mistake. Let's see if I've got here. Yeah, sorry about that. Thought I had fixed this. I was working very late at night, so I missed out a little bit. But in order to get 1 here, you're going to have to apply our lowering operator to that thing. And destroying the one creating a 2 is what isn't necessary to get there. So I have a 1, 2, 2 plus a 1, 3, 3. And this one down here is the same thing but with a minus. Now these guys down here are right. That's a combination of 1, 2, 3 and 1, 3, 2. All of them are those combinations. This one being square root of 3 over 2 plus 1/2 of this. That then in the P department becomes a minus 1/2 plus the square root of 3. So that these two right here are orthogonal to each other. And then that's also true for the mu equal minus 1/2. The only difference between this and this one is the spin here has been turned down. And that's also true for these two right here. And for these two as well. The spin gets turned down for the second state here. Doesn't affect the orbit tableau or numbers. So the one that comes down here has a very similar structure to this, involving square roots of 2 plus or minus. And then finally, at the very bottom, we have sort of the opposite of this state. Okay. So this is all the effects of having a p orbital that is not coupled up to 0. Here it's coupled up to give these triangular t-square sort of tableaus. In any case, that's just a rough sketch of how we look at the Pea Shell when we're able to kind of divorce the total spin from the total orbit. So this would be called LS coupling model in an elementary book, which would probably not discuss things with 3 electrons, simply because that becomes really problematic without this mathematics. And before it became problematic even for calculations, because the use of coefficients of fractional parentage is a real hair puller if you have to do it by hand. Obviously computers have taken over, and so people don't even think about these atoms anymore. But we should. Okay, so what I want to do here is try another way of looking at this. This, as I say, only at the end of the lecture will I try to show this very complicated coupling that's hidden behind this symbolism where I draw a certain thing about the orbit and a certain thing about a spin very separately and treat them separately. I have a total spin that I believe is a good quantum number, actually is slightly tarnished quantum number in a real atom, and the orbit also a tarnished, slightly tarnished quantum number. Only the total J is going to be a good quantum number for these orbits, and then only if we can ignore any spin of the nucleus, because that causes hyperfine interactions that are really very fine structure. So what I want to do now is say, okay, let's let them really get married. Let's get them, so we're talking about, instead of LS coupling, what is usually called JJ coupling in modern physics textbooks. So let's do it. Here's the basic idea right here. Just what kind of states are we going to use? Well, they're going to be, basically count them, 1, 2, 3, 4, 5, 6 separate states now that are not broken in half. They are married to their spins. The electron is now proud of showing its spin. It is holding it, and it's very important to it. And we have then to use letters A, B, C, D, E, F instead of the numbers that we've been using for the orbits, 1, 2, and 3. And then arrows up and arrows down for the spin as before, but now they're attached to the actual, shall we say, orbital part of the electron. So that's something new here. Now, what's the group theoretical name for what we're doing here? Well, we have a supergroup that encloses, that is greater than, a little curve greater than sign, U3 cross U2. So we're doing quantum mechanics now on 6 equivalent, more or less equivalent things. Okay, so U6 is the order of the day here. And if we're going to do U6, we're going to need tensor operators to go with it. Before, with our orbit, we had 3, so we had to come up with 9 operators. That's 8 if you don't count the identity operator, which doesn't do much but sets your origin. So here, with 6, we got 36 tensor operators to play with. Okay, the 9 from there, and then the 4 that come from having this extra tensor there for spin 1/2. That's dimension 2 squared is 4. This is then being multiplied by dimension 3 squared, which is 9. So we're ending up with a chart, if we want to look at every one of these, of 36 tensor operators, each one of them 6-dimensional. Okay, so that is the unitary calculus that's behind this particular quantum mechanics. So JJ coupling is, in that sense, a higher level of physics than the one that ignores the spin-orbit coupling. Okay, so here are the protagonists. There's the orbital part there that consists of the 8-fold way, if you will, of U3, plus the identity that no one pays all that much attention, but the information people, of course, have to pay attention to all of this stuff. And then the U2, the spin part, which has only 4 operators, as I say, 3 of which get to come out in polite company, but there's always, again, the phase of the spin that we have to worry about. So this is going to take care of it all, presumably. Now, building the outer products of these operators, for example, and one of the things I've done here, and it may be a little difficult to see, is instead of putting the minus sign next to the number where you usually do it, I stick it on top. So the -1 that should have gone here has got itself into a position of a hat. for the one. And remember, this was a minus one before. That's the way it's drawn now with a hat. This one doesn't have a minus sign. This one does, sort of opposite to this one, and these are the tensor components. We're not so worried about tensor components in this case if we're going to do spin-orbit calculation, which we're not, because I failed to get all the phases right, so I'm not going to show you my work on that yet. But we're just going to talk about it. And this one right here, the 1, without the hat on the subscript, and this one with the, and this is what's hard to see, is there's a little hat sitting on. That is necessary if we're going to be putting charts of this thing and compressing it down to lower level. And I'm trying to find all sorts of tricks on math type to let us do this. And one of the tricks I discovered is to make an array within an array, so that you actually see the little 2x2 arrays that are from the U2 getting their little positions located out and sitting on top of the positions associated with the 9 dots that are in the orbital part of it. So the orbital part sort of dominates here, and then the little spin parts go onto these regions right here. So here you see a product of 1, 0 from the orbital part, that's this thing, having its cross product with the 1, 0 that goes with this thing right here. So this comes down with a 1 and minus 1. Remember, that's the Z angular momentum operator up to a factor. It should have a 1/2 plus and minus. But we're keeping it, so it's just 1s. And it's 1 and minus 1, and it sits there. And then down here is 0 right in the middle. That corresponds to this 0. And then this minus 1 here is going to affect that same thing. So it becomes, instead of 1 minus 1, becomes minus 1, 1. So that's the diagonal part. And then off to the side I have a 1, 1 bar. I'm using the 1 bar thing from this guy right here. There he is, okay, with his little negative sign that he's getting from this guy right here. And this one's doing, I think, a similar thing over here. You see those two little U2 matrices taking up their place on the real estate that's commanded by the orbital U3. So this lets you get a feeling for what the U3 cross U2 is going to be giving us in terms of computational real estate. Okay? So I've got to give elementary names to these cross products. Here I'm actually explicitly writing it in the mathematician's way of writing it. V orbit cross outer product, Kronecker product is actually the correct name for that. And then 1 minus bar that comes from that little guy right there. That's what's making this matrix right here. So this is a raising, or depending on how you look at this thing, lowering operator for the U6. And there's 35 more of them. That's, you know, pretty daunting. And this is only the Pea Shell. Okay, 3 states, 2 an electron, right? So you see, you know, all those atoms that we're breathing, and then the big ones that we're holding in our body, they're pretty complicated suckers, right? They're amazing, absolutely amazing. We haven't gotten to the molecules that they, of course, make, but we'll be doing that shortly. In any case, we need to make an elementary operator out of that. And that's pretty easy to do if you use the A, B, C, D, E, F notation here. Just have to find out where you are on this axis, A, B, C, D, E, F. We all know the alphabet pretty well, so this is not too much more difficult than counting. 1, 2, 3, 4, 5, 6. But if I were to use numbers, I would really be in trouble right notationally, because I'm already using those numbers for the orbit apart. So this is the best I can come up with as far as computational machinery. So over here on this side of it, the EBC, the transpose of that is CB. And then the transpose of DE there is also being shown. So that's the notation. We'll be getting to that soon enough. And of course the notational complication is pretty you know, if you're going to be writing these things a lot, you like make that easy too. Okay, so now there's one thing here I want to show, but we're not going to really make use of it. But it's such a in my mind, it's one of those things that just goes and makes a picture of the problem here, the whole enigma that's associated with spin and orbit. And it's called the assembly formula. That's what we gave the name of it, because it assembles these two different physics, the different physics of the orbit. So thinking of states like we've been dealing with, this is just an example of the use of this assembly formula. It's in that paper that had the jawbone formula for U3 and higher unitary groups. This is where the spins and the orbit are allowed to keep each other at arm's length, and that the symmetry and anti-symmetry of either one of them is up for grabs and a separate entity. And then the so-called Slater determinants, the things that actually say, by George, we have to obey Fermi-Dirac Pauli and make them anti-symmetric, make the total anti-symmetry a law as far as each of the particles that have both orbit and spin are true. So I never can have two entities in this column here that are the same. If I have two numbers that are the same, that's okay as long as the spins are different. And if the spins are same, I better have the numbers different. So in that sense, the anti-symmetry is ruling here very clearly. What's not clear is how the anti-symmetry is ruling here. Doesn't look like it is. It looks like they're always free to do whatever they want. But that's not true, because there is a relationship between each of these states as indicated by these numbers in the column here, which is what this assembly formula computes. And it's not a difficult thing to take them apart, that's disassembly, or assembly, put them back together again with right numbers, and make a clearly threefold transformation matrix. 2 over the square root of 6 with a minus sign, 1 over the square root of 6, 1 over the square root of 6. That's a very E-like C3V symmetry vector there. And of course there's a completely scalar vector that goes with this arrangement. And then these two down here are the orthogonal to that, also common. So those are things we've already seen in a number of contexts. So this matrix here is a matrix that comes very much from symmetry mathematics. Now, it's every number, this is 3, there's 2. 1, we don't worry about this stuff. But 2, 3, 4, 5, 6, we've got these assembly diagrams. These are the ones that have everything going for that particular thing. This one right here is the what we would call the orthostate. Here we're allowed to have a spin tableau that can have angular momentum other than 0, and here we're not. That's the para state. The way I remember that is the orthodox. Orthodox things are things that are more common. Paradox, that's more unusual, right? So para goes with that which has the least amount of spin, hopefully 0 spin if you're talking about 2 objects. But here you kind of have this one right here being quite ortho, okay, lots of spin. This one's sort of, you know, para or meta, I don't know. You know, if you're going to use Greek, you're going to get in trouble, but a lot of people do. They do give Greek names to things with different spin. We'll be tackling that issue with respect to molecular superfine, hyperfine structure. But here we're just talking about the plain old LS structure of atomic spectra. And this is what you get when you have 2 electrons playing with each other. And it's pretty neat. There's usual matrix we get for C2 symmetry. This is more like a matrix for C3 symmetry, but it's tableau symmetry that's really giving this, and then 4, 5, and so on have assembly diagrams like this. Okay.
Dr. Harter?
Yeah.
You would always have to specify the spin in the end tableau?
This always have to specify.
Like the spin with the arrows? You always have to do that, right?
Well,
Or you can
it's
just, like,
really
get away with-
convenient to do it for U2, because there's only up and down. Now, what are we going to do when we start talking about nuclei that have spin 1? Right? There's going to have to be an up, a dot, and a down for that. Right? If we're going to play this game the way we've been playing it with spin 1/2. So that will be a more complicated, and then you'll be able to get more complicated tableaus like we're getting for the orbit. So when we talk about something that has, say, 3 particles, each with spin 1, right, then the spin's going to be able to play as strong a game as the orbit does, and there'll be, you know, a lot more, so the box will be bigger. Does that answer what you're after? Now, the other thing that goes with your question.
What about, can you, like, for example, like when you want to, like, describe, like, more degrees of freedom of a molecule, like the isospin or something like that, you can still
As you
use
do in nuclear physics.
You can still use the
Then you'd be doing U4 here,
Yeah.
right? You'd still have the same sort of thing to play with the orbit.
And the
If
same
it was
with
a
the
P,
color.
if it was a P, D,
flavor.
F, yeah. And they use the same notation.
Is
You
this,
go and look at that, what I call the most dangerous book in the room there. It shows all the level diagrams for the isotopes.
yeah.
Okay, with the gamma rays just coming out. I mean, things glowing over there right now. Just don't look at it. It's dangerous. But that's what you're doing, right? You're playing U4 against whatever orbit you might have. And if you get me afterwards, I'll show you. I've written a couple of papers that actually did that. That was where Wigner got started on all the spectroscopy. The Wigner super multiplet model of nuclear mass. And I had a tiny little thing to it, and a lot of group theory that he, of course, didn't have available to him at the time. So yeah, that is a very doable thing, and there the spectra is of masses. We're talking about millions of electron volts, billions of electron volts. Okay, now the Pea Shell spin orbit collection, you'll notice there's not a whole lot there, and that's because I still really don't know what the heck is going on with some of the details of this marriage and unmarriage. So we'll presumably get to that a later lecture. Now, one of the things that we're going to have to do is deal with a morass of Clebsch-Gordon coefficients. So today, I've left you a annual gift of the reviews of modern physics. Now, they're not actually giving this anymore, but I've managed to get hold of an old copy and scan it in. And this takes you through Clebsch-Gordon coefficients, starting with the ones you already know. So actually, some of you may have gotten a hole punched right through the paper at that point, but that lets you put it in a notebook. I think you know this 1/2 cross 1/2 Clebsch-Gordon table. It's just 1 over the square root of 2. It's just our assembly formula for the simplest case, symmetric and antisymmetric, the ortho and the para spins. Okay, so if that's got a hole punched through it, it shouldn't bother you any. I thought it was better than putting a hole through some of the D functions that they very kindly give with this table. But in any case, we're going to have to work with 1 cross 1/2, 3/2 cross 1, 3/2 cross 3/2 would be fair game for us as we try to look at spin orbit a little bit more closely. And as we try to look at some of the hyperfine stuff that comes up in the molecules, it's always good to have a very nice set of tables, all sort of compacted things. Now, if you look on the internet, you can find Clebsch-Gordon coefficients, but they'll go on for pages. So it takes you a long time to find the table. Here they're all in one place. So I think this is better than the best I can find right now. Okay? You can thank me later. So, what a gift, right? Okay, now we have to come back to the basic idea of what it is we're doing with respect to the state labels, which are analogous to the lab-based group operators that we used to talk about when we were talking about molecular rotation. But now it's just electrons that we're playing with, going around and occupying different states, or electrons are, the way their view is, that they're sitting there and they're covered, they're afflicted by various states. So that this is just a review of lecture 20. There's the link back to it, and probably more links working to carry you to various places on this thing. The basic idea is just to think about the orbital wave function coming around and getting attached, as it were, to the different particles. Particle A, particle B, particle C. I'm now using the letters to designate the actual victims of whatever the disease or affliction is, and that's the, in this case, p orbitals, 1, 2, and 3, in our immediate discussion here. Okay, so the real punchline for all of this was that only relative position counts. This is a battle or a marriage or whatever you want to call it. We are assembled here for, we can't tell whether it's a marriage or a funeral, and there are some marriages that are like that. But the main thing is the reaction of the two people, right? And then, or it should be. Of course, it rarely is, so that's why it turns into a funeral sometimes. But the idea here is that only the relative position of these two things, the states and the particles, counts. So this is just one more manifestation of the Mach principle that I like to make fun of for group theory, for transformation theory, for wave function theory in general. So we will make use of that enough before we're done today to maybe have you thoroughly hate it, but let's go for it. So once again, and this is stuff that goes with the link that is in the previous pages, where I say very clearly, here are my cats. They're going to describe the states. That's nothing new. We would normally just write that. But here it really does help to let the particles know that we care about them. Even though they're all identical, we still love them. And we put A, B, and C at the lower right-hand corner of the kets to celebrate their existence. Because it's going to be a transformation of one with respect to the other. Now, if you're just worried about it, say I have a little typo there, S sub, I'm just talking about sub-tableaus, the subgroup tableaus. Here we have a group that permeates A, B, and C. That's the D3 or S3 group. Let's go back to S2 subgroup that just had A and B. The C hadn't come along yet. And so there, we're demanding that particular transformation, A, B, is picked out and special. It's the first two letters, should go with the first two numbers of the states, that we demand that the eigenvalues associated with those permutations represent symmetry for a horizontal tableau. And if the C or the 3 is there, fine, but this is just between A and B. And then when the A and B are in a vertical, or 1 and 2 are in a vertical position, this is going to be antisymmetric. So this is just that subgroup chain labeling that permutation group theory has done automatically. Whereas the crystal groups, you kind of, oh, you can pick this one to be diagonal, pick that one to be diagonal. No, you can't here, not have the whole big formalism work. It's already built into the mathematical theory, the subgroup chain. That is, it comes 1, 2, and then 3 is the next one. And that ordering is what makes a symmetric group and unitary theory powerful. So we are trying to respect that as best we can. So the next stop then would be to look at the other permutations. And we really only have to look at one other permutation, and that's the one between C, and we might as well use the number 2 or the B letter as the next thing to look at. So if we've already agreed on this subgroup chain, then C is next, and we might as well do it as the two next numbers next to each other, n and n minus 1. In general, if we're talking about Sn, we're going to be looking at the permutation n minus 1, the bicycle. So this is an incredible formula that Yamanouchi found. Okay? And you can see that it works very well for giving us here minus 1 over d, where d is that weird hook length difference, the city block difference between box n and box n minus 1. Quite the same d that we were using in that Jawbone formula for the unitary n to n minus 1. This is clearly related to that, but proving that is not easy. I have not completely facile with the relationship between those, but it's really amazing is if I get bigger and bigger tableaus with bigger and bigger hikes between the n and the n minus 1 box, look what happens to the matrix. This thing gets smaller negatively, this one gets smaller positively. As the d goes up, it's 1 over d. Here, 1 over 2, that's, you know, pretty close to this, you know, the largest number you're going to see on a diagonal. Here's the largest, 1, okay, where you just have one box. But here we're talking 2, okay, for the distance between this box and that box right there. So that is the thing. And this one has to be minus and this one has to be plus for this formula to really work. Now, if it's n minus 1 sitting over n, that's a minus 1. If it's n sitting next to, n minus 1 sitting next to n, those are the only two possibilities in a tableau. They have to be going up as you go this way, and they have to be going up as you go down on the columns. So these are the only two possibilities for adjacency, where you get 1 or minus 1. But when you're talking about a distance, the bigger that distance goes, the smaller. It's like a Coulomb potential, getting smaller and smaller and smaller as you get bigger and bigger tableaus, with bigger and bigger city block hikes between them. And then this thing approaches 1. Okay, that's this guy right here. Okay? That's, I mean, there's something going on here, right, that we don't completely understand, right? But the beautiful formula, right? Because once you have this, then you have all of representations. You just cycle them through. Next thing would be n minus 2 and then you put those two together and make what you've passed over, just like we did with the e's, the elementary operators. Okay? Is that all right? You can see, I think, perhaps Bala, you can see that there might be, there's a glimmer of hope that this might be a help in some sort of information, quantum information setup, you know, some sort of thing. But there it is at work. Here's a S5, permutation 5, looking at 4, 5, okay? And you can see we're down to a quarter here.
Was it developed by Yamanouchi? Is he
Yamanouchi,
Yamanouchi, is he the one?
Japanese
Oh,
mathematician.
okay.
Yeah. Yeah, you see, he took over kind of after, well, the Jung, Alfred Jung, the inventor of the tableau,
Yeah.
was a minister in Britain in sort of the Victorian era.
Okay.
It was a long time ago. Okay, and he conceived of these things and saw that they were useful, but he didn't come up with any of the hook length formulas. He just went off on some algebra that, got the field started. But the Japanese seem to be the ones that really did the best job of getting formulas that show this is a powerful calculus, really powerful. As I've said, it's the most powerful mathematical notation that I, as a physicist, know of, and we treasure it. Okay, so just to get us back on the track for something we already know, well, I think we've all, almost if we've been looking at this for very long, memorized all 3 factorial representations of the E-type. That's the tableau that has the right angle. And we certainly know what the scalar, A1, that's the horizontal tableau, and then the vertical tableau, the totally antisymmetric to totally symmetric sides. This is the in between, neither totally symmetric nor totally antisymmetric, that you get for 30 things, third-rank tensors in particular, for what we're doing. Okay, so I want to use the projector that comes from this to actually build the things that we've been drawing here, particularly the ones that have tableaus for orbit and tableaus for spin separate. And then how does that thing manage to get it together to assemble the Slater determinants? We'll almost get the answer to that, but not quite today. But here's the basic idea. Here come these projectors that have, and remember, I always told you, go ahead and write the indices that you get for your one-dimensional projectors. Even though they aren't going to be 2x2 or 3x3 matrices, they still do have indices that are the same, at least in the physical interpretations. But here, we're taking advantage of the fact that this projector is only going to be being used on kets. So we're going to name our boxes by the index of order that is associated with whatever this box contains, and it contains state numbers. So I'm going to be putting numbers on the tableaus to the right that are going to work with this, and so the particle labels are going to be confined on the right-hand side of each of these tableaus here, you see. So we've already been through a collection, and this is where the hard part is. This is pretty easy here with just one-dimensional things. Totally symmetric. All the permutations have a 1 in front of them, a +1. And then totally anti-symmetric. All of the even permutations have a +1, but the odd permutations, the bicycle class, gets to have a minus for this. And that's what it means to be totally anti-symmetric as far as this projector business goes. So somehow we're going to be able to make all of these states have Pauli anti-symmetry. And that's a little bit of a job that we need to finish out today here. So if we can get that through today, I will consider an otherwise failed day to be a success. Okay, so let's go for it. Now remember, we really took advantage of the right and left indices here when we were looking at wave functions on a triangular, or actually we had a hexagonal lattice where they were very telling. And then as you go to higher symmetries, it gets even better. We haven't really gotten there yet, but we've already seen that it makes a difference whether you're talking about the internal, shall we say, the body-based symmetry, or the external here. Kind of got that maybe a little turned around here because aren't the particles on the inside? But no, we kind of have the particle thing sitting out on the outside, and that's because we're going to get ready to sum over those things and make them disappear completely. And that's really important because they do not actually have an identity. They are the most unidentifiable things, those electrons. You see, the A's, B's, and C's are history after we get done here. They have to be. The states, we can pull on those and change those. You can't grab a particular electron. It resists that. It just doesn't have a real physical identity. The only thing it has is its spin. If it can hold that in one direction, then it's got a label, but that's temporary. You see, so identical means identical in physics. Just as every wave in a perfect wave tank is identical to the one next to it in an ideal isotropic wavefront. So this business of inside and out has to have a few more words said about it. Okay, so we're going to go ahead now, and this is the projection on orbits that we just looked at, where the Yamanouchi formula gets. Yamanouchi formula is also going to be used, same P operators, but now on spin. Okay, the first one's easy, and this is the one that actually produces the angular momentum, 3/2, 3/2. So the calculus of angular momentum deserves to have this kind of notation, helps to have this kind of notation. So here we come, and we're talking about the spin state, and we're talking about a totally symmetric combination of that. So we're going to go through and sum up all of these guys with the same phase, just get one state. There isn't anything more. Now, you should note that this projector right here has antisymmetric parts, and the AB or the BC or the AC, if you apply the antisymmetric operator with those letters, you get nothing, and so the E projector is not going to give us anything unless one of these spins, at least one, is turned down. So in the next slide here, and let's keep the more or less in track with each other, the next slide here is to look a little bit talk a little bit about the antisymmetric A2 projection. The A2 projector fails on all spin-half states. Every one of them. It just can't live. It's not going to happen. Okay? And you're talking about applying it to the spin state. You just can't get anything. Does not exist. Does not exist. Does not exist. Because you've got 3 boxes here. This A2 projection for 3. And we are talking about S3, so we're playing with that kind of box there. The antisymmetric one, the A2 one, is the old-fashioned name for it. A1, oh boy, we really love that one, but we just hate this one. Okay? Because at some point, I go 1/2 spin up, and then I got to have a different thing in the next box that's down, and then I'm out. I got to use either the first one or the second one. No way. So that's what kills it. It will never show up. This is a forbidden symmetry for this 3 particle system, and the A2 is verboten. But we can do lots with the A1, and E is where all of the action is, so we don't have anything lost there, and that's what we have to do next here. Okay? So here is the result, a result. Okay, and now I'm just doing it on 1 spin turned down. I'm going to do the 3rd spin turned down, and I'm going to apply this projector, and that's not 0. Okay? Well, a couple of them become equal, so I collect them and change the normalization accordingly. Then down here, going a little bit further, here I've got the symmetric one, A, B, C, that we know and love up there, working fine on this one as well. But then as I apply these, well, I get some different kinds of vectors here. Going through, I put the same numbers in that I've been putting in here for a 1-1 projector, and I collect them, the ones that are the same, and then I change the normalization denominator accordingly. Then I do it with this one, and I end up here with a, so this is a familiar pattern. This is a 2, -1, -1, and then that's normalized to square root of 6 denominator, and then 1 and -1 normalized with 2 of those, so I'm ending up there with square root of 2. So these are the two orthogonal states made by the separate projectors. This one here is still A, B, C on the inside, but on the outside, this outside guy right here, A, B, C here, A, C, B here. So these have to be orthogonal states if they're not, if they exist at all. But both of them are spin a half and spin up total. Okay, there's more up than down by 1, so this has got a positive a half there. Putting the angular momentum values in as an afterthought is what this allows us to do and get right. Okay, so there are two spin a half states that we've seen here that have m equal, well, plus or minus 1/2, as we'll see, but that one of them has spin 3 halves. That's the box that's laid out, and then this angular box is giving us a total spin of 1/2. We got that one essentially for free. We didn't have some very much for that one. Okay, so all three of these states project from this particular one. Spin up, up, and then 1 down. And the left J labels of the last two make a particle doublet. Those are the two that I was referring to. This and this being A, B, C. You can see it more clearly on that one than you can on this one. A, B, C, and then A, C, B, reading the way you would read a page, is the second permutation label. Okay, but still, this is just, now we've taken care of up, 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 up. That's what we got there. And then we got up, up, down taken care of. Okay, we're sort of half done, a little over half done. Here's the thing sort of pushed up to the top of the page. Okay, and that's just saying I'm making the last double, repeating myself. Okay, now I want to point out one of these things. This is invariant to symmetric subgroup projector. Okay, well, one of them gives you 0. So this thing right here, this one, that antisymmetry, gives you something that is equal to its minus. And if you're equal to your minus, then you're nothing. So the AB that comes from the inside symmetry here will hit this thing, and AB is in a vertical box, so that's death. That's death for that one. Okay, I wanted to make that clear. So this is where the inside, the side of the projector is having to pay attention, as it were. Now, let's see if there's anything new here yet. A, B, A, C, A, B, C. I think that's it. But in any case, this is the one where we project not up, up, down, but down, up, up. And those are in the latter part of the tableau. So there's more chance for us to get to use the one that had the thing in up and down. So we get states that are not too different, except that now the -2, which was at the beginning, now shows up on the end. And the same thing, these two show up in the first part instead of the latter two parts. Okay. Again, making orthogonal states. We're making a complete set here of orthogonal states for these three spins. And finally, the fourth state here. Okay. Okay. So we've done a very exhaustive symmetry projection for the spins And before that, we did a fairly exhaustive, same sort of exhaustion for the orbit. You got to put them together. How do you do that? Okay, put them together and make it a Pauli Dirac Fermi, right? Antisymmetry. Okay, so that is what. Now remember, we've got it so that the right index really does correlate with state permutation. That is, whether the two spins are equal, and the left index correlates with particle permutation. That is, whether we're talking about the same A, B, and C, as though we could ever find that. So this is where we're going to have to be doing the summation over this one to get rid of the A, B, and C labels. They just have to go away somehow. Okay. Now, these orbital tableau states, as I say, 10 pages above where we are now. We haven't gone very far in this lecture, have we? Time passes fast when you're having fun. Okay, these must be combined using the actual permutation Clebsch-Gordon coefficient. This is something we really have been very much amiss in describing in this class. We're just going to show it very quickly here, but the Clebsch-Gordon coefficients look very much like the angular momentum coefficients for spin 1/2. So it shouldn't be too terrifying. Anyway, in the following simplest case, this is a single term for each state. I don't have any argument with that because I have clearly got antisymmetry tied up in all three particles by having it be symmetric and then make the orbital part antisymmetric. So no argument there, and I don't have any A, B's, and C's that are shelling, so I'm okay. But we got to do something about this business here, because there are A, B, C there, and A, C, B there, and so forth down here. Okay, and so this is where you use the Clebsch-Gordon coefficients that come from the finite group S3. You use the ones that produce the dreaded A2 symmetry. Well, it's the desired A2 symmetry that Fermi, Dirac, and Pauli are asking for this 3-electron system. So that is really what's going on here. So I am busy here summing with the using the sub-indices that actually represent the tableaus A, C, B, or A, B, C. That would be the A. This one would be the big B. This one's just the opposite. Here's the big A, and there's the big B. I need to do those. And those are just square roots of 2. 1 over the square root of 2 and minus 1 over the square root of 2. So in this case, it's pretty transparent. And when I'm done, I've got a thing that I label like I have these things under control and that it's antisymmetric, but you can't see by looking at that it is. You have to go in and examine what happened when I made this sum here with plus 1 over the square root of 2 here and minus 1 over the square root of 2 for that guy. And I did it for both of these, okay? Both the one that had total spin 1/2 and minus 1/2. This is a big jump right here. This is where the A, B's, and C's disappear. This is, to answer your question from last time, how in the heck do I get antisymmetry out of things that aren't antisymmetric? Well, I wish I could do it clearer, but this is about as clear as I can make it at this point. Okay, so this is the climax of this terrible lecture right here. Okay, we're going to do a little bit more with it, but I just want you to see that that's where the formalism takes us at its current state. And it's kind of a big deal. There was a spin projection, and now we're putting it together. So this really says it in that sense right there. This is how permutation, multiplicity, and ABC levels disappear. Killed by Pauli. Okay. And he's kind of a mean guy, so I can believe that he would do this. Okay? But the spin generation, all the things that the physics allows, is still here. Okay? And so are 8 orbital doublet pairs, the octet. It's made Pauli-OK for this unitary group, giving us the multiplicity of 8 for all those 3 orbital tableaus. They're all making something that's totally antisymmetric. It just doesn't show here. It disappeared when we do that. That's the best I can say at this point. Now when you do Slater determinants, you know it from the beginning. You put the spin right on top of the guy, stick it in a determinant, and it's a crazy piece of mathematics because basically you just have all these things that are totally antisymmetric. You get a pile of them, right? If you had a lot of electrons, right? And I go in there and I move 2 things. The whole thing turns to a minus. Its phase turns to minus if I just do any two, right? Now where else do you see that? In mathematics, where you see it are the antisymmetric forms that are using exterior calculus. You go in there and change any one of them, and a minus sign pops up. For the whole thing.
Kind of like
And it's pretty obvious it does it. That's what a determinant does, right? You switch one row. I don't care how big that thing is, the whole thing is now minus.
Built into the mechanism.
Yeah. Flip 2 rows. It's minus. Oh, but you can save it, flip any other 2, or those 2, you're back home with positive, right?
Actually,
It's
there's a
so
way to
easy to
write-
change the sign.
there-
It's so sensitive to that.
There's a way to write the determinant of a matrix using you know, like they have like the big pi. You know, like that big pi, like the one that you have like products.
Hmm.
So there's a way to write like the determinant as a wedge.
Yeah.
You can
Right.
notice there like
It's,
the wedge
it's
is-
a generalization of the Levi-Civita
yeah.
tensor,
Mhm.
right?
Because like with the
And
big
there are
pi,
lots of
Yeah.
Levi-Civita tensors, right? They as big a rank as you want. Most of us are used just to 2 rank. Right,
Yeah.
right. That's the nice little
with
SU.
the big pi,
3, 4, 5 rank epsilon tensors, right?
Is that not the distinction between the unitary and the special unitary? If the special unitary has that,
You're right that it is in the sense that the
Invariance.
determinant is being watched, right, for the special, and be demanding to be 1, right? And soon as if you do that, then you're preventing any of those sneaky flippers, right? Parity changing, you might call them, operations. But probably what you have more in mind is the antisymmetric metric that goes with what are called the symplectic transformations, right?
Oh, I
That's a
asked
whole
about
nother
that.
Lie group,
it
right?
is. That's why I'm.
SP, and it's always even, right? Because your metric has to be off diagonal, 2 by 2, right? So you can only make 2, 4, 6 number SP. There's no SP3. Maybe there is in Trump world, but there's not in the real world. Okay.
And that could be considered a negative dimension in some way for another.
Imaginary, maybe. Yeah, I don't know. I mean,
Latest-
most of the time when we
latest
say a
bets in-
dimension, you're allowed to go plus and minus with it. And if you're in a
This
place where
might
you're
be new.
restricted to the positive, like you think you are in spherical coordinates, right? You think you're restricted to positive R. Of course you aren't. There's a whole other sheet, right, for things that have gone through the origin.
There is a.
The topology is actually quite weird when you get at it from that point of view. It's what is responsible for some of the stuff we were seeing with the go around the 2 pi to 4 pi.
Mhm.
All of this stuff has glimmers of connection.
Stoyanovich talks about things in terms of invariance, and so he describes the U spaces in terms of the Kronecker delta,
Mhm.
and then when you restrict it, you're also using the antisymmetric Levi-Civita
Mhm.
tensor as an invariant as well.
Something that's made an
On top.
antisymmetric invariant
On
is
top of the other.
very much a part of the symplectics. So it must be that if you have a big enough unitary group, you could stick in a symplectic group as a subgroup. That could be, yeah. In other words, U4 could have an SP2 without bursting its seams, right? Perhaps. I'm not sure. Yeah,
Yeah,
I'm not
that's-
sure.
Where did
I
you
know
get
that
this?
SP2 and SU2 are in some sense morphic. I don't know if it's actually isomorphic and maybe homomorphic.
It's
But anyway.
that dimensionality
Um,
sign.
This is real quick here, and we really do want to quit a little bit early today. This is where I wanted to point out that if you use boson operators for these things, it works. Okay? You go ahead and use the boson operators the way they're intended to use, and you've got a symmetric thing, it seems to work. And I think I've proved that it works for all. I think Gelfand had proved that a long time ago. But most of the time, when we did our destroy and create, we just adjusted the norms. When we got two things, we made room for it, changed the norm, right? Got a square root of 2 for raising, lowering operator, right? Instead of just 1, right? And other times when it didn't make a new term, we just left it with 1. Well, this does it automatically if you follow the rules of the n plus 1 and coefficients there. Whichever is larger always gets to be the one that gets put on the outside there. Now, connecting this with angular momentum is kind of interesting. I took the and I'm using this abbreviated notation here. Instead of going a dagger, right? It's as I said, impolite to bring weapons to the dinner table. I think it's probably impolite to bring it to mathematics. So there are no daggers here. The dagger's been taken off of the creation operator because we use it the most, and you just have to write one letter. And maybe a subscript because you've got more than one kind of particle. And then this thing, which we don't use that much, the destruction operator used to not have anything on it, right? And we put a bar. So that's a compact notation you'll see in modern text now. And
So they
I
use
don't take
that
credit
now?
for that.
They don't use dagger for creation anymore?
Well, the mathematicians have to write it a lot. They got tired of writing, and so they don't. The physicists?
Yeah, because like
Yeah.
I found myself like writing a bunch of daggers, and I think that's a waste of time.
Right. Do it this way, right? It's a waste of pencil, right? Graphite. It's wasting graphite if you're doing it with pencil, or ink if you're doing it with pen. Yeah. So, yeah, it makes sense. Anyway, matrix elements for the elementary operators. That's or it's got an A bar and then an A if you're doing the destruction. Okay. So now you think of the destruction operator, it's got this big weapon over it now still. It's got a bat, right? It takes a bat off and destroys the thing, right?
Gotcha now.
Puts it back on.
I'll never remember that one.
Okay, so that's what, anyway, we've seen these matrices before, okay? We did this another way, but I just don't have them ordered in quite the way, but they're good, okay? And you can go ahead by taking products and conjugates and stuff, you can make super elementary operators out of these things. And when you do that, you'll kind of be doing in a smaller space what we've been doing here. But this will produce, this is just to make a connection with angular momentum, as opposed to stuff here which really has not had angular momentum sullying its day in court, as it were. You can go ahead and take this matrix and build very easily from those combinations L plus, that's E12 plus E23 times square root of 2. I was going to get that on there. Okay, and then L minus is just a conjugate of that, so it flips the indices. There's nothing complex here, so you don't have to worry about that. And then you just put them together, L plus L minus times LZ minus 1, and you've got L squared. Okay? So you can go and look at any matrices you have, or the numbers that you actually see here, which are mostly 6s. Here, 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 and here. So there's 4 6s. But here we don't quite know. We have to diagonalize that. So when you do that, you find out what the angular momentum states are that are going to come out of this particular really simple tableau. Which you kind of breezed over. We should have gone back and done it in a little more detail. But here are the projection operators. 5 of them give you a 2 for angular momentum. And that's good because that's what the dimension of angular momentum 2 is. And then the other one gives me, this one's the one that gives you the doublet of the D orbital. Okay? This is the one that gives you the other guy, the L equals 0, that goes with this thing. That's implies the S orbital the effect that has that. So this, and I'm going to push this all this stuff up to the top. This right here gives you the Klipsch-Gordon coefficients for this particular coupling. So with that, I'm going to cut this nonsense until we figure out more about the Pauli principle, which we really want to do before great experiments show the impressive physics that such a monster of Fermi and Bose both can dance as it is meant to dance. Okay.